or something. That's what happened.
So I always bring my laptop. That wouldn't help in this instance.
Usually this doesn't happen. I think
It's a bad signature.
yeah. All right. Back.
Slideshow, and again, maximize the minutes.
Yeah. All right. We're back. Yeah, we're back.
We're back.
Okay. Thank you.
Sure was.
Thanks so much. Nobody, right?
Okay, everybody, we're back. Take your seats and we'll continue.
You want the lights on?
Yes, please. So good evening, everyone. Jeremy, thanks for the introduction, and it's great to be here. So Jeremy already gave my first disclosure that I'm not an astronomer, astrophysicist, or aeronautical engineer, so bear with me. The second disclosure is I've been a NASA ambassador only since February. Done a number of events. They've mostly been solar observing events and around the Parker Solar Probe and the Punch mission. This is my first presentation. So I beg your patience and understanding, especially since it is Friday the 13th. So tonight, what I'd like to do, and it'll be hopefully new to at least some of you, I'd like to cover a number of things in this talk on Europa and the Europa Clipper mission and the search for habitability in our solar system. So first, just talk about the question of looking for life elsewhere in our solar system and the issue of habitability. Where do we look and why? We'll talk about some moons in the outer solar system. And then we'll move to Europa and why it's such a good candidate to consider for habitability. And we'll go through the physics, the geology that's available, all that we know about Europa, the current hypotheses and models we have and what the limitations are. And then I'll shift to the actual Europa Clipper mission. And parenthetically, I'll mention some things about the European Space Agency's JUICE mission, which is kind of the sister mission for this one. And we'll go through the mission specs, the engineering, how it was designed, what the objectives of the mission are, and the instrument package that is suited to do so. And what are the very unique challenges that NASA engineers and scientists face with a mission to the European system that's different than many of our other past missions. And then finally, at the end of the talk, we'll get a little philosophical. And we'll talk about the role of Europa Clipper and other planetary probes as sort of ambassadors for humanity. And this mission in particular is very appropriate. And then I'll close with some remarks about projecting what the next 3 decades may be like in terms of missions that are either on the books or planned to address the issue of habitability and the search for life elsewhere. Okay. Not good. So first of all, what life is and how we recognize it. The simplest definition we have for life, just to start with the basics, a self-sustaining, self-replicating molecular or chemical system that's capable of Darwinian evolution and passing on genetic material to the next generation. That's based on life as we understand it in all forms on Earth. So then you ask, how would we recognize evidence for extraterrestrial life? And you could spend a presentation just on this. So we can talk about looking for extant or extinct life very close. In this case, it would be Mars, be the perfect candidate. We're sort of doing that already, fiscally, God willing, okay? And there's a lot of potential there that we would find certainly extinct life, but also bear in mind that even though it's very dry and arid and bombarded by heavy radiation because of its lack of a real thick atmosphere, Mars has substantial amounts of subsurface ice in the equatorial polar regions. It has huge amounts of liquid water in its mantle, at least based on seismographic data we have. And there are areas in Mars, especially in lava tubes, lava caves under the surface, where you would be shielded from radiation. And existing extant life could possibly exist. We could study exoplanets. We're now 35 years since the first exoplanet was found. Now we have first Hubble, now the higher resolution of James Webb. We can look at, now we have 6,000 exoplanets, roughly. Several hundred of those are terrestrial in nature. A fraction of those are in the so-called habitable zones of their either M-class or yellow stars, like our own sun. And an even smaller fraction are believed to have stable atmospheres. So using Hubble, James Webb, we can look at those atmospheres. And now with advances in transmission spectroscopy, we can look for signatures, so-called biosignatures. That is chemicals that would be produced primarily by a biologic system, though not necessarily solely. And this is great. It's in its infancy, but if we were to find a really compelling biosignature, to try to send a probe or any other device to check that out and confirm it, even with the best technology and a craft that could move it near light speeds, which we don't have, obviously, it could take many, many decades to hundreds of years. You have a similar problem when you talk about SETI, certainly looking for signals from elsewhere. Low probability, low risk. We've been doing it for 65 years with SETI, then cosmic, now laser SETI. You have to look at the right place, right point in the sky, at the right frequency, you may find something. But what if we find a non-random artificial signal? We confirm it multiple radio telescopes. Again, moving at light speeds, if we were to try to send a response, whatever that would be, could take centuries or thousands of years. So let's be practical just for a second and say, where could we look using current or near future technology over the next, let's say, 3 to 5 decades to find not only habitable worlds, but potentially, and I always have to underscore the word potential, actual life elsewhere. And if you ask that question, 2 other questions emerge immediately. What are the key prerequisites for life as we understand it? And where within the confines of our own solar system would be the best bets to look for? Complicated answer, but actually quite simple. Follow the water. If you think about it, all life as we know it on the planet requires 4 key ingredients. You have to have water, you have to have essential inorganics, as well as carbon, usually nitrogen, phosphorus, a sulfur source, not necessarily oxygen, but those key organic and inorganics. You need to have an energy source. It could be the sun. It could be chemolithotrophic energy, which I'll talk about later, where you're breaking down minerals and rocks, generating organic substrates using a chemical and a heat gradient to produce, material that life could survive off. But most importantly, you need time. You need stability, okay, for the really complex processes of molecular and chemical evolution to occur to eventually get a stable self-replicating system. Everywhere where we look on Earth, where there are these elements, we find life, and it usually is thriving. Extremes of temperature, pH, salinity, pressure, absence of light, presence or absence of oxygen. We find so-called extremophilic organisms that survive. And this is important because they provide case studies for us that potentially elsewhere, even within our own solar system, under the right ingredients, even under harsh conditions, life could possibly exist. So, where do we follow the water? If you look at the available data we have, this big surprise is that the majority of water in our solar system is not on Earth, and we're primarily a water planet. If you look at all this available data, which has been updated quite recently, there are a number, the outer moons of the solar system, that have copious amounts of water as subsurface oceans, as well as have some other very desirable features, right? Now, among these, if you look at the absolute estimated volumes of water in these worlds and the percent volume of the total mass of the world, there's really 5 candidates that jump out. And they are Europa, Ganymede, and Callisto, 3 of the Galilean moons, and we're going to focus tonight on Europa, and then Enceladus and Titan of Saturn. These are worlds that are the best candidates. And all of them are changing our ideas about what habitability means, because these worlds are all far beyond the habitable zone. Except for Titan, none of them have any kind of real atmosphere. They're usually called exospheres, okay? These are harsh worlds. So I am going to focus on Europa, but I'd be remiss if I didn't mention a little bit about Enceladus and Titan, the amazing data that was obtained from the Cassini-Huygens mission. And I'll mention at the end of my talk some missions to these two worlds. So Enceladus is a relatively small moon of Saturn in mass. It's only about, I think, the 20th biggest moon in the solar system. Nonetheless, evidence, gravimetric, radiometric data suggests that it has a subsurface ocean that is tidally heated by Saturn. It has active surface geology, remodeling the surface. We see evidence for volcanic water plumes, so-called tiger stripes, especially in the southern hemisphere, that it's been detected: hydrogen, nitrogen, CO2, even methane. So very suggestive. And available gravimetric data suggest Enceladus has geothermal or hydrothermal vents, like we have here on Earth, and I'll show you a video of that later. Titan is almost equally more amazing because it's probably the closest analog we have to our primordial Earth. Here you have a world that has a dense hydrocarbon-rich atmosphere, only about 1.5 times the pressure of our own atmosphere. The chemistry of that atmosphere is believed to resemble prebiotic Earth, based on the Cassini-Huygens data. It also has a precipitation cycle, but it's hydrocarbon, primarily methane-based rather than water. There are liquid lakes of methane and ethane on Titan that actually have tidal and seasonal variations. And again, it has a huge subsurface ocean. So these are all candidates, great candidates, but we're going to focus on Europa because the general consensus right now is it is probably the best candidate for habitability and possibly even finding life. There are currently 2 missions that are ongoing to the water worlds of the solar system. The Europa Clipper mission I'm going to talk about, but I'd be remiss if I didn't mention the European Space Agency's JUICE mission. Just very briefly, how they're similar and different. The JUICE mission is probably, well, no, clearly, the most advanced, sophisticated mission the ESA has ever sent as a planetary probe with a state-of-the-art instrument package, really phenomenal. It was launched in 2023 on an Ariane 5 rocket, and it's on its way, an 8-year mission with 4 gravity assist to the Jovian system, where it's going to make 12 flybys each of Ganymede and Callisto, the Jovian moons, and only 2 of Europa. That's a really important point that I'm going to come back to several times today. Because Ganymede and Callisto, while having oceans, possible candidates, they are very far, not only from Jupiter's gravitational influences, although it's there, but more importantly, the punishing radiation and magnetic fields from Jupiter. Okay, that's a big difference between this mission and Clipper. Aside from that, the instrument packages are both state-of-the-art and very comparable in their scope and functionality. The mission objectives are the same. These are really sister missions, okay, that in the 2030s, if they're successful, will be amazing. But that difference, going to Ganymede and Callisto and only 2 flybys of Europa, makes a big difference on the mission planning and the engineering that goes into Clipper. So just so everybody's on the same page, I think we all know what the Galilean moons are, discovered by Galileo in 1610. First objects to orbit another body in the solar system other than the sun. We have Io, the most volcanically active moon in the solar system, something right out of Dante's Inferno in terms of a hellish world. And then we have these 3 moons, all of which have subsurface oceans, but very, very different geology, physics, and overall profiles. Again, Callisto is an old world, heavily cratered. It has water, probably doesn't have very much tectonic or any kind of surface remodeling. Ganymede's the biggest moon in the solar system. It has an enormous subsurface ocean. It has craters, It's old in parts, but it also has some young surface. So there is probably some geodynamic or tectonic type remodeling. And then there's Europa that I like to call the Goldilocks world because it's just in the right place to make it a good candidate for habitability. So let's just focus a little bit on Europa for the rest of this part of the talk. So here we have a moon that is about the size of our Earth moon, 90%, has a high albedo. It's tidally locked around Jupiter, around 3.5 days. And what you'll hear me come back to again and again, it is subject to punishing gravitational forces from Jupiter and punishing magnetic radiation from Jupiter, okay? And this affects not only the profile of Europa, but again, our design of the Europa Clipper mission. So what I'm going to try to do in one slide, albeit a busy one, is summarize for you about 50 years of what we know about Europa. And then I'll talk off of this the rest of this talk. So in the early 1970s, ground-based observations suggested that Europa was like a dirty snowball. That's what it looked like. Water ice with patterns on the surface. The Pioneer and Voyager probes confirmed this, provided higher resolution, and showed that, yeah, you see this kind of features, but there was very few craters on Europa, which suggested a younger surface and some kind of, again, geological or geodynamic processes. Hubble blew away the scene with the types of imagery we're able to get from Europa. And the Galileo mission in the late 90s or early 2000s was spectacular because it made 12 close flybys of Europa and gave us a substantial body of knowledge. First, a relatively smooth surface crust with these ridges or lineae, as they're called, and freckles or spots throughout, which seem to imply, again, active geology. Surprisingly, we found that Europa had its own magnetic field, but that field was not because of a rotating molten core. That field was induced by Jupiter's magnetic field and interacted in a very delicate way with Jupiter's magnetic field because Europa had an electrically conductive fluid interior. A very fancy way of saying it probably, if not almost certainly, has an ocean. Hubble and now James Webb confirmed the presence of cryovolcanic activity on Europa, just like Cassini found on Saturn. Water plumes, geysers that erupt from the surface up to 120, 150 miles into space. But yet, despite all this, we knew that the surface was rock hard and really cold, 110 to 150 or 60 degrees Kelvin, but an icy world. In the last 5 to 10 years, Keck observed from these plumes that there were certain inorganics of considerable interest on Europa. Sulfur, CO2, oxygen coming from the radiolytic breakdown of surface water, and various peroxides and oxides, and even some water vapor in the tenuous atmosphere, which we call an exosphere. So the current model was real simple. Europa has a thick icy crust and a subsurface ocean. Well, let's look at some of this geology. What does it mean? How does it affect now what is our current model of Europa? And what does this mean for the question of habitability? So when you look at some of the surface features here, while Europa is about the same size of the moon, it looks really different. Rather than craters, you have these long linear features or cracks called lineae that can be several miles wide, but stretch for thousands of miles on the moon, and not just in isolated spots, all over. When you look at it, it almost looks artificial, like someone did a really bad job crocheting the surface, right? But this is what you see. And it was suggestive there's some kind of active geological processes that are causing this fracturing on a moon-wide basis. The next interesting feature were these substances called lenticulae, from the Latin for freckles, okay? Round or elliptical spots or pits on the surface that the best theories are subsurface water is erupting through the icy crust and bringing with it reddish sulfur, possibly iron-based minerals. The water vaporizes into space, the minerals deposit on the crust, get bombarded by solar radiation, micrometeorites, and we see these freckles. And they're not isolated, they're all over the moon. Again, something's happening beneath the surface. Craters, or I'm sorry, chaos terrain. This is really an amazing feature found on Europa. These are areas, look like ice rafts. Sorry.
It's always the opposite way you think.
Yeah, it's the story of my life. These are ice rafts on the surface, and they're areas where pieces of the crust have broken, undergone upheaval, tilting, rotation, even lateral movement, and then refroze. Definitely suggesting some type of underlying convective process or tectonic process. Interestingly, we have chaos terrain on Earth. It's in areas where new crust is being formed. I saw it firsthand in Iceland. It looks really otherworldly, very much actually like this. But again, the implications being some active geodynamic processes are reshaping the surface of Europa. And then the last bit of evidence is the craters, or the scarcity thereof. I'm showing you one. It was actually recently spotted, the Puy-2, beautiful crater. But by and large, we have a moon here that's about the size of our moon, yet there's less than 50 documented craters on the surface. The moon has around 5,000. So what it was suggesting, or has suggested, is that much of the surface is very young, 30 to maybe 180 million years, a babe in geologic time. And that there is absolutely active remodeling of the surface going on to have such a smooth surface. So if you put together all of these data, the gravimetric, the radar, the magnetographic data, the geologic data that we got from Galileo, more recent observations, you come up with the current model of Europa. It has an icy crust, 10 to 15 miles thick, but that crust is not uniform. It has different ice layers with different physical chemical properties, to the best of our knowledge. It sits on top of a 40 to 60 mile deep ocean, the density of which and exact composition of which we don't fully understand yet. And that ocean interfaces with a rocky silicate-rich mantle, which we believe is undergoing active geological activity, and which feeds the ocean with inorganic minerals and salts that cause its electrical conductivity. And then you have a core, a metallic core that I think the best guess right now is it's nickel iron. But that core, again, is not producing Europa's magnetic field. It's the electrically conductive interior, the ocean, as a result of the impact of Jupiter's magnetic field. So what does this model tell us? What does it imply, especially about habitability? Well, first of all, and this still blows my mind, the water, the amount of water. A body about the size of our moon has twice the amount of water of all of Earth's ocean. And we're a water planet. Just get your mind around that. That's like mind-boggling to think that that's possible, right? And so the next logical question then becomes, well, how does the water stay liquid? And I think you all know the answer. Basically, it's tidal frictional heating. So when you consider Europa's mass and its proximity to Jupiter, it undergoes intense gravitational interactions, tugging, pulling, and then retraction. You have this kind of gravitational tug of war that creates massive amounts of torsional tidal heating. And the current best estimates are this tidal heating is sufficient that the oceans are not only liquid, some scientists speculate that parts of them may be pretty temperate in temperature. More importantly, we know that due to the tidal heating, this mantle, and certainly the upper parts of it, are undergoing a lot of geological processes, probably cryovolcanism, strong convection events, probably hydrothermal or geothermal events that are all contributing to very active remodeling of the surface. And I'll show you some of this. But here's the most important point, and you'll hear me say this a couple of times tonight, and that is Europa is subject to stronger tidal heating forces than the other Galilean moons, Ganymede and Callisto. And by relative comparison with Enceladus, given its smaller mass, much more strong tidal heating than Enceladus. And so the implications are it is more geologically active and for much longer periods of time than the other Jovian moons and even Enceladus. And that is a really important consideration in considering habitability. So let's look at some of the consequences. Now, these are artists' conceptions, not the real deal. If we look at tidal heating, where does it impact? Well, it impacts the mantle, as I said, the ocean, these ice layers, a more fluidic ice layer, as well as a colder, harder outer layer. And where tidal heating particularly comes to play is at the interface between the ocean and this warmer ice, where strong convection coming up from deep within the planet passes through this more fluidic ice and eventually either through or causes cracks in the harder outer shell. And when you get these eruptions of water, you see these plumes, these cryovolcanoes that have been observed from space. You get those lenticulae, those spots or features, freckles where mineral salts have been deposited on the surface. And the current thought is that this kind of convection may cause, in part, not completely, these long linear fractures or ridges, the lineae that stretch for thousands of miles. So this is cool, but what's more interesting is this little artist representation right here. And that is what is the effect of convective heating on the chaos terrain that we see on Europa. And the current, again, the water is coming up from below, creeps through the more fluidic ice and goes into the icy layer. And what most recent observations have shown and the most recent theories suggest is you get the formation of these little submersible lakes or water inclusion bodies in the icy crust. This is very disruptive because what happens is parts of the icy crust break apart. They undergo upheaval, tilting, rotation, and active lateral motion that is very disruptive to the existing surface features. So you can think of this as tectonics, only it's with water and bits of icy crust and not molten magma and rocky crustal plates as on Earth. But conceptually, it's the same thing. And the current model suggests that basically this outer crust is floating both on the more warmer fluidic ice as well as the subsurface ocean. And this process is very dynamic in that the entire outer crust makes a complete rotation around the moon about once every 12,000 years. So this is a really, really active world. And again, we don't understand everything about these processes, but this is just the data that we have so far and the hypotheses that have been made to date. Now, lastly, we have hydrothermal vents. And I mentioned to you that we believe these exist on Enceladus, and most likely based on the radiometric and gravimetric data that we have from Europa, they likely exist as well. I don't know if any of you know about these. This is not Europa. This is, I'm going to go back and restart it. This is on Earth. Geez. Yeah. This is the basis of the Marianas Trench, about 7+ miles down, no light, extreme pressure, and yet you have a thriving ecosystem. Okay, and the basis of this thriving ecosystem, wish this would work, it doesn't seem to be.
You have to click inside the video.
Oh, let me try, here we go. You have this thriving ecosystem, and at the base of that ecosystem are these extremophile microorganisms that we classify as chemolithoautotrophs. And what that means is that these microorganisms metabolize and break down inorganic sulfur and iron from the rocks and soil and sand grains on the bottom, and they generate organic material for nutrient. And that process is powered by the heat and chemical gradients from those smoker vents that you saw, which are pumping out high pressure, highly acidic, very hot, super hot water that's rich in minerals into the surrounding ocean. Now, I am not implying that this is what exists on Europa, and there's lots of life forms swimming around. The whole point is this is a case where these vents exist on Earth. They were discovered only about 40 years ago. Scientists still don't fully understand them. But the point is that where the right ingredients are present, even under really extreme conditions, in this case, extreme pressure and depth, life doesn't just exist. It flourishes. It finds a way, to quote Jeff Goldblum, right? So if we think about this then, and we put all this data together, the data from Hubble, Keck, James Webb, Cassini, with Enceladus, all the data from Galileo and the best theories, what we know about hydrothermal vents, what we know about chaos terrain on Earth, we come up with a grand hypothesis. And the grand hypothesis is Europa has all the essential ingredients for life. It has a high probability of habitability, and it actually has a fairly high probability that there could actually be life. And the reason is simple. It's got all the ingredients. It's got the water. It's got the essential inorganics that all life needs. It has a stable and abundant energy supply, huge amount of tidal heating, as well as surface radiation processing, driving these geodynamic processes, geothermal vents, convection processes, remodeling the surface. And very important, it has time on its side, stability. I said to you before, Europa is subjected to stronger tidal heating than not only the other Jovian moons, but even relatively speaking, than Enceladus. So it's not only been more geologically active, but for a long time. Estimates about 4 billion years. All the right scenarios, if you will, for life, or certainly habitability, but possibly life. Now, an important thing to always stress here. All of this, these are hypotheses based on data, based on observations. And like any branch of science, you generate data, you make observations, you make hypotheses to explain it. Those hypotheses are not fixed in stone. They're not immutable. In fact, they're supposed to be tested, challenged, refined with new observations and data. And that's exactly where Europa Clipper comes in, okay? Its intention is to generate a substantive and really incredible body of data with both remote sensing and in situ instruments to challenge and test and refine our existing hypotheses, to answer the unanswered questions, and probably generate many more questions in the process. So that's the lead-in, the remaining half of this talk, to the Europa Clipper mission. So if you remember nothing from this whole talk, remember this. Europa Clipper is the most technically advanced technological mission, both in the spacecraft and in the instrument package that NASA has ever designed for a planetary probe. And it's probably, again, the counterpart of the ESA's JUICE mission. First confirmed or approved in 2015, it was launched only about 8 months ago, almost to the day, October of last year from Kennedy on a Falcon Heavy, fully expendable rocket, weighing in at just about 6.5 tons for the whole package. And right now, it's on its way on a 1.8 billion mile trip to Jupiter, not Europa. This mission is not a Europa orbital mission. And I'll say it again and again, this is because of the punishing radiation and magnetic fields that would be associated with that. The risk factors of the mission would be extraordinary. And so instead, Clipper is going to go to Jupiter, 6-year trip that it'll arrive in 2030 following 2 flybys, or gravity assists, sorry. One from Mars that just took place the end of February, 1st of March, and the second, an Earth gravity assist in late December of next year. And then when it reaches the Jovian system and integrates into a stable orbit, the plan right now is approximately 49 meticulously detailed flybys of Europa over the 3.5-year mission of the Clipper. And during that time, as I'm going to show you in subsequent slides, the trajectories are such that will minimize the time that Clipper is exposed to the damaging, punishing radiation fields from Jupiter, while maximizing the time for its state-of-the-art instrument package of about 10 instruments to do as much data collection and acquisition and sending to Earth as possible. With the goal of the mission broadly being to determine the astrobiological habitability of Europa, not to look for life, just whether it's habitable, and secondarily, to look for possible landing sites for a proposed Europa lander mission that, given the way things are right now, if it does happen, wouldn't happen probably until late 2030s. So this is the broad, big picture of the mission. Now let's just get into some little details here, put everything in context. How big is Europa Clipper? So when we look at it relative to the Space Launch System, the Statue of Liberty, school buses, SpaceX, heavy launch, you see it's pretty big. It's about 100 feet long, 58 feet wide, roughly the size of a basketball court. And you can see pretty obviously that most of the size are these enormous high efficiency solar arrays, which need to be that big so that at Jupiter distances, you can gather sufficient sunlight to generate power for the electronics, the subsystems, the instrument package. Well, I want to just focus in on those a little bit. These high efficiency solar panels have also been radiation hardened. I don't know the process, but that's what I've read and been told. They were made by Airbus, a Dutch company, and then sent to Kennedy for final testing and assembly. And you can just see the sheer size. This is just one solar array relative to the techs and the engineers. And each of these panels is about 190 square feet and can generate 150 watts of power continuously when pointed toward the sun at Jupiter's distance. If the craft is in a shadow, there are lithium-ion batteries on board that have been charged from when it was in the sun. So the point is the subsystems, the electronics never will lose power. There should be no interruption of power to any of the machinery or the instruments. Again, for context, this is Clipper minus its solar arrays, minus its high gain antenna during final testing, assembly at JPL, where it's undergoing a multitude of system checks to make sure everything is perfect before it's sent to Kennedy, or was sent to Kennedy, to combine with its antennae and its solar arrays. And again, just for context, you can see the size of the craft relative to the techs working on it. It's a big beast. And here, again, for perspective, is an artist's conception of what this may look like in orbit. And I show this to you really to point out this area here, which I apologize, it's a little hard to see. This is the propulsion module. It was made by Goddard Labs. And it's basically carrying 6,000 pounds of propellant, of hydrazine and dinitrogen tetroxide propellant. And that propellant is to feed 24 thruster engines that are in a round configuration, each of which is able to produce about 25 newtons of force. And why this is important is that when Clipper gets to Jupiter, sometime in April-ish of 2030, there will be a 6 to 8 hour burn of these thrusters that will use up probably about 60% of the propellant in order to slow down the craft so that it can achieve a stable Jovian orbit. The rest of the propellant will be used for the thrusters for attitude control, subtle modifications in propulsion if the trajectories of Clipper need to be modified for any reason. So then we ask, okay, what's the objectives of this mission? Well, again, astrobiological habitability of Europa, not really to look for life. It's going to study with remote and in situ instruments the thickness and properties of the ice shelves, as well as the ocean and their interaction, a much more detailed, in-depth assessment of the surface composition, much higher resolution of the surface geology, and actually, given that this world seems to be pretty dynamic on the surface, to look at specific areas and see if things are different than they were 30 years ago from Galileo. Very importantly, it's going to look at the subsurface, really look at those geodynamic, geophysical processes that are going on, cryovolcanism, convection, again, hydrothermal vents, all of which are affecting the geology you see on the surface. And then lastly, it's going to be a scout. It's going to look for spots where a lander that'll be AI-directed, autonomous, to land, stay on the surface a while, make detailed analyses of the surface and the subsurface. So if you look at the instrument package that makes this possible, again, it's state-of-the-art. All of these instruments will be firing or operating simultaneously on each flyby, again, for maximum data acquisition. And again, I mentioned this before, this instrument package is quite comparable in multiple respects to the same kind of remote sensing and in situ instruments that are on the ESA's JUICE mission. So let's just look at some of these, because I know there's probably engineers that really love this kind of stuff. So if we look at the remote sensing, you have two spectrometers, an ultraviolet and an IR spectrometer. And what they're going to do is look at spectra that it's coming through the atmosphere, the very thin atmosphere, the water plumes, okay, on the surface, or surface ice and dust. And they're going to look for fingerprints of inorganics and even organic substances. This imager, this high-resolution imager, basically is going to provide both 3D and color mapping with a resolution of about 1 meter. So we should get much better surface detail with this imager than we have from past. The thermal imager is kind of obvious. It's looking for hotspots or heat plumes, both in the outer crust and even if it can penetrate a bit into the more fluidic basic crust. And then this ice penetrating radar, as the name suggests, is really going to look at the thickness and the properties of the ice shelves, both, and how they interface very dynamically with the subsurface ocean. Then you have these in situ instruments that are really a complement to the others. The mass spectrometer and the SUDA are essentially going to complement what the spectroscopy units do, in that they're going to directly sample parts of Europa's exosphere, the water plumes, and dust and ice that are ejected off the surface, because Europa is heavily bombarded almost constantly by micrometeorites. Magnetometer, pretty obvious. You want to understand better Europa's magnetic field, how it changes as a function of the density and the depth of the ocean, and importantly, the electrical conductivity of the ocean. And finally, you have this really important gravity science experiments or instrumentation. It's going to accurately assess tidal heating, not just in the ocean, but especially in the ice shelves, the upper mantle, and more importantly, the very dynamic geophysical interactions and chemical interactions between these various layers to produce what we see on the surface. So this is, again, a data gathering machine. Okay, it is basically how it was designed. And I show you this very quickly. This is just an artist rendition of the instruments, their positioning and their orientation on the spacecraft. Okay, nothing else to say, just where they are and how they're positioned. So I've mentioned many times now about this, the punishing effects of Jupiter's magnetic field on Europa. And the whole design, the whole engineering of the Europa Clipper mission has been because of this very magnetic personality of this moon. Basically, as you can see here, Clipper is going through one of the most punishing radiation fields in our solar system, only next to the sun. You have Jupiter's magnetic field, Europa's magnetic field, in this very delicate dance. And as Jupiter's field spins, it acts as a giant particle accelerator. And unfortunately, Europa bears the brunt. So again, this is why we don't have a Europa orbiter mission, because that was considered at one point. It is why, again, Clipper is different than the JUICE mission because Ganymede and Callisto, where that's going to be the bulk of ESA's mission, their effects of these magnetic fields, it's not zero, but it's greatly reduced. So again, this affects the whole design and engineering behind Clipper. So NASA scientists and engineers use 3 different really clever approaches, okay, to try to circumvent some of this punishing radiation. The first thing, shielding. They built a vault of aluminum, titanium, and zinc at quite considerable cost and mass to shield just the most sensitive, radiation-sensitive instrument packages. It couldn't do everything, but just the most sensitive package on the spacecraft. Secondly, the state-of-the-art instruments were designed with a property that I had never heard of this before, and I presume it's pretty new, and the instruments are self-annealing. Now, at the risk of anthropomorphizing machinery, what this means is that by little subtle bursts of power to the different instruments, basically they can heal or repair from acute radiation damage, provided it isn't too severe. And the analogy that was made to me is, if you had a cut, an abrasion, even a burn on part of your body, and it wasn't so bad, you'd be fine, you would heal, you probably wouldn't need medical attention. A worse lesion, different story. That's the analogy here, only with the instrument. A way of healing or keeping healthy in spite of radiation. And then the last thing that engineers did was some really incredible Herculean design and plotting of orbital trajectory and dynamics, so that during its 49 flybys, Clipper spends a minimal time in the most punishing areas of Jupiter's radiation fields, while still having maximum data acquisition capability. And that's shown here in this cartoon. So again, over the course of 49 carefully orchestrated flybys, Clipper will come anywhere from as close to 16 miles from Europa's surface to several hundred. And during that time, all the instruments will be fully active, again, maximum data acquisition, but the spacecraft will spend less than 24 hours with each flyby. Then it zips out, and 2 to 3 weeks, you repeat the same process again, another flyby. 7 to 10 days after a flyby, Clipper has to send back all the data that it gathered. And that's simply a precaution in the event of catastrophic mission failure, or if something should happen to the telecommunication equipment, you will only lose the data gathered on that most recent flyby. All the others would have already been sent to Earth. Let's hope their calculations are correct. So it's been estimated that using this kind of design and process, we can get about 3 times more usable and effective data from Europa by Clipper than if we were to use a different kind of process that would have a much higher risk of radiation-induced damage and potentially system failure. So lastly and importantly, when Clipper is going through these 49 flybys, it's going to have multiple gravity assists from Europa itself, as well as Ganymede and Callisto. And each of those gravity assists will result in just slightly changing the trajectory of the flyby, so that with each new orbital flyby, you have a new closest approach of Clipper to Europa, again, to maximize global coverage so that all the instrument package can do their job best while still minimizing radiation exposure. And if you follow this out, after 3.5 years and 49 plus flybys, you get this very colorful, artistic thing called an orbital pedal plot, just to show you the complexity and the dynamic nature of the already calculated flybys. Now, having said all of this, despite all this technology, despite really amazing engineering on the part of NASA, this is still a really high risk, really dangerous mission. Okay? Really high risk, really dangerous. The accumulated levels of radiation, even with all the 3 precautions that I said to you, are considerable. And this little cartoon, again, shows you the orbital trajectories. And with each orbit, this little Geiger counter is ticking the estimated radiation exposure. Well, the total cumulative radiation over 3.5 years and 49 plus flybys is a little over 2.8 million rads. That's several million X-rays. So again, technology and engineering can do so much, but at the end of the day, prayer is a good alternative as well, because this is nasty. And again, no diminution of the ESA's JUICE mission. Amazing, but it's not dealing with the same magnitude of a problem going primarily to Ganymede and Callisto and only having 2 flybys. So, not to be a downer here, let's leave this aside in the last couple of minutes that I have. Talk about not science, not technology, but something a little more philosophical. And that is, since the very beginning, all of our planetary spacecraft have been sort of ambassadors for humanity. Not my quote, someone else. Just in case that these incredibly well-designed and well-engineered machines that are quite resistant and could spend decades, if not even centuries, in space, even when their power supplies are low. Just in the event that they would be encountered by an intelligent alien civilization, we want to basically let them know who we are, a little bit about what we're about, where we're from, why we sent this piece of machinery into their neighborhood, and that our intentions are benevolent. For those of you, and probably most of you given the survey, that are old enough, you probably remember the Pioneer plaque from the 1970s. This was really controversial. It's this gold anodized aluminum plaque that have a naked man and a naked woman on it just to show what we look like, and they're not holding hands because we don't want ET to think that, you know, we're connected that way, right? But you have these images. You had spectral lines for hydrogen, hydroxyl, and water, an atomic clock, some mission details, and even a little schematic where the craft came from, where it was headed to, just in case. The Voyager missions, which we now, they're both in interstellar space, right? They took it a step up. 2 12-inch records, phonographs, gold-plated copper plates that had etched within them messages in just about every human language. Sounds of wildlife, sounds of nature, mission details, all etched into the copper plate, even with a mathematically based code and a stylus to tell the aliens how to read and listen to the record, just in case. Okay? And now, let's currently take the Parker Solar Probe, which I know a great deal about. Here you're going into the most punishing thermal and magnetic environment in the solar system, okay? Through the sun's corona, coming within 4 million miles of the surface. That probe has over 1 million people's names etched on it, as well as messages and greetings. It even has a microchip with a 1958 manuscript on heliophysics that Eugene Parker, the person the probe is named after, wrote to talk about the solar wind, just in case. Okay, so it doesn't come as a surprise that for a mission like Europa, that's addressing the question of habitability and maybe even life elsewhere, NASA was going to want to engage the public. So there is, or was, this message in a bottle campaign where they invited not just the 4,000 or so people that have worked on Europa Clipper over the last years, but the public, if they wanted to send their name to the European system. 2.6 million participants submitted their name. They're etched, engraved in a microchip that's embedded into a tantalum metal plate, along with a whole bunch of information that I'll show you. And that plate is in Clipper's vault, that shielding vault that I mentioned, engineers designed to shield the most radiation sensitive equipment. And you can see this is what these plates look like. So on the inward facing side, you have the message in a bottle, chip is embedded there. There's some other mission details that aren't really legible here. You have a beautiful poem in praise of mystery, a poem for Europa, written by the US Poet Laureate in her own handwriting. You have the Drake equation, written in Frank Drake's handwriting. Radio waves for hydrogen and hydroxy, pointing to the great watering hole. And a picture of Ron Greeley, a now since past planetary geologist who did the really seminal work on Europa's geology based on the Galileo data. And then on this side of the plate, you have the spoken word for water in 104 different human languages in the form of human voices that are embedded as waveforms. It's a lot of stuff packed into this plate, just in case. This is the poem, pretty amazing. Not going to read it. It could not just be for Europa, but any water world where you're looking for habitability or life. But I have to read you the last 6 lines because I think they're pretty profound. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark. Well, I think E.T. would like this, okay? And if I was an alien civilization, I don't know how you could say who we are, what we're about, where we're from, why we sent this probe, and that our intentions are peaceful any better than this poem, and especially these last words. So we're on our way. We are 8 months to the day almost since Clipper was launched. It's on its way to the Jovian system. So far, trajectories are all good. The recent Mars gravity assist also is very beneficial in that it gave engineers a chance to test and calibrate a number of the instruments, in space, and they all were functioning beautifully. So far, so good. You can follow this mission on any number of different social media platforms in real time. And if you want more information about Europa, the mission, or you want to participate in some citizen science initiatives, this QR code will take you to more information than you could possibly want. So in closing, the very last slide. I'm an optimist and pretty passionate, obviously, about astronomy and planetary science, but I think it's fair to say that the decade of the 2030s and then the next 2 that follow will be an unprecedented time in planetary exploration, especially in understanding habitability and potentially in finding life. Let's think about it. You're going to have, unless they have system failures or something horrible happens, you're going to have the data coming out from Europa Clipper and JUICE in the early 2030s. Huge amounts of data. By this time, we'll know whether we're going to have a Europa lander mission, probably in the latter 2030s. In addition, 2 other missions, really big, are on the books. And this is why I told you a little bit before about both Titan and Enceladus. NASA's Dragonfly mission has just completed systems review and it's been given the thumbs up. This is a mission to build a nuclear-powered quadricopter drone, shown here as an artist's conception, that will be flown to Titan. And when on Titan, in its atmosphere that's only 1.5 times the pressure of ours, it'll be able to do vertical and horizontal flight, and it'll study that prebiotic chemistry of Titan's atmosphere. It'll study the precipitation cycle, the rocky, icy surface, as well as those hydrocarbon lakes. And most certainly, with remote sensing, it'll probe the huge ocean underneath Titan, again, for signs of habitability. Even more almost science fiction-ish is NASA's Orbilander flagship mission to Enceladus. This is a proposed concept. It's got a price tag of about $5 billion. And it's supposed to launch in 2038 and will get to Enceladus around 2050, 52. The reason why it's so cool is that it's going to go to Enceladus, and for 1.5 years, it'll circle the moon. It'll do all kind of remote and in situ sensing of the surface. It'll fly into the plumes, the way Cassini did, sample the plumes, but here, it's not looking for composition. It's looking for signs of life. It'll have the systems on board to actually look for life. After that, the probe will land on Enceladus and be there for 2 years and conduct in-depth analysis of the surface and the subsurface And it'll do so using what's now under development, these incredible AI-directed, autonomous, intelligent robotic systems called EELS. Exobiology Extent Life Surveyor. And as the name suggests, these are snake-like segmented robotic systems that can go on a terrain. They've been tested in Arctic and Antarctic and Iceland and many different kind of terrains. Explore different kind of terrains, make observations, collect data. These are being designed to go to those volcanic plumes on Enceladus, go through to them, and go into at least the upper part of the subsurface ocean. And again, not do compositional analysis. These are going to look for life. So I mean, it's pretty, again, I think fair to say the next 30 years, the questions of habitability in our solar system will be definitively answered on one or more moons. And I think there's a good probability, a good betting chance that we may find the first signs of life elsewhere in one or more moons. A great time to be alive. I just wish I was 30 years younger. I'm not sure I'm going to be around. And so with that, I will close and take any questions you may have.
That was fantastic.
Oh, cool.
One of my very favorite
Oh, good.
projects. That's terrific.
Just send money. I'm kidding. Yes.
How would the mission want to end?
If you could wait for the mics, that way they can hear us on YouTube.
It's a really good question. So two outcomes.
How will the mission end?
How will it end? So the fuel's going to run out, the propellant, but let's just say NASA decides, as it often does, that it'll extend the mission somehow. So engineers may find a way, even though the solar panels won't work anymore, to use it for something else. The most probable likelihood is that Clipper will be crash landed into Jupiter or Callisto or Ganymede. It will not be crash landed into Europa. And contamination. And it's the same if you recall from the Cassini-Huygens mission, it didn't crash into Enceladus. It burned up in Saturn. Okay. And I think that in fact, the mission director about a year ago said they'd actually prefer to crash land it in Ganymede. Because at the time that would be happening, the ESA's JUICE mission will still be there, and it may help with some of the surface geochemistry studies that are going to be done on Ganymede. Because Ganymede, it's Ganymede, Callisto, and a little bit of Europa. It's mostly Ganymede. So that's how it'll end. If it doesn't extend, it'll crash into either Jupiter or probably Ganymede. Yes.
I'm gonna stay on one side if I can for a little while.
Why exactly 49 missions?
It's a great question. Yeah, and I honestly don't know. But my best guess from talking to a couple of people is, again, I said, this is already a really high risk mission, right? Radiation exposure. And don't forget, Galileo only did 12 flybys, so 4 times. And I think NASA being NASA and wanting to be bold and adventurous, but also conservative and not have mission failure, they don't want to push their luck too much. I think the calculation is that 49 flybys or thereof, approximately, given the precautions that have been taken with shielding, self-annealing, the orbital trajectories, more than that, we're pushing radiation damage that could cause mission failure or just not being able to send back data. So I think that's the best guess.
Or is it just money that they're allocated 3.5 years and that's the number that
Well,
they get?
I'm not allowed to talk about political things, so
All right.
I have to hear it. But the last budget that I saw, which is not finalized, this is not being cut. So for the foreseeable, I mean, it could be, who knows? But so far, it's still safe because it's a mission in progress and it has a lot of potential. I mean, can you imagine if the United States found life in another world? Come on, right? So it kind of has a political value. So I think Clipper may be one of those that will be safeguarded from some severe budget cuts. That's opinion. Yeah.
At that distance, why would you use solar panels or use a reactor?
Great question. I thought the same thing. So first off, the Juno mission provided proof of concept that at Jupiter distances, if you had the right size solar arrays, you could power the subsystems. And this is newer solar technology than was used on Juno. NASA did an in-depth analysis of that question. Do we use solar arrays or do we use a plutonium-powered radiothermal electric generator? And the outcome was the solar arrays would be more cost-effective and practical. I think practical is NASA's way of saying, if we can avoid at any cost sending plutonium into space, especially in a world where we want to assess habitability and what happens if it crashes, I think that's why they leaned toward the solar arrays, because they knew they would work. The only thing that the solar arrays contributed was more mass, but it still was within mission spec. So again, it was, how do we mitigate risk or potential risk if this craft were to crash and it's carrying plutonium and it goes into Ganymede or Callisto or Europa, any of these worlds where we think there could be habitability. So that was the reasons. Yeah.
Somebody over here had a question?
After the two gravity boosts, what's the speed of the crash?
The number I saw, don't hold me to this, I think it's about 39 to 40,000 miles per hour. And that's why you need to have that burn when you get to Jovian orbit to really slow it down, or you're just gonna, even with Jupiter's gravity well, you may just overshoot. So yeah, it's about 40,000 miles per hour.
Thanks.
Anyone else? Yeah, have anybody on YouTube with questions?
I
Anybody?
didn't see any last I checked. Nope, don't see any.
Good. Well, thank you. Thank you.
I'm way more impressed with that mission. I was impressed before, now I'm even more impressed. That's amazing.
Especially when you consider, the obvious challenges. I mean, NASA does a good job. They have problems, but they do a good job.